What the hell is that? Oh, okay. Okay, strong. Are you guys ready? Okay. Dylan, strong.
I'm pretty sure that it doesn't have the conjugate base.
It does have a conjugate base. It does. But the conjugate base is so weak it cannot act as a base. Okay? The strong part, a chemical species that does what? Katie. Ionizes or dissociates 100%. I'm going to say dissociates because that's part of the Arrhenius language. Dissociates 100% in solution. And then what about the Arrhenius acid part? Aditya. Yeah, it dissociates 100% in solution to release H plus ions. Yes. You need to have something like, you could say a strong Arrhenius acid dissociates completely in water, producing H plus ions. That would also be fine. Okay, it just something along the way. This dissociates fully, dissociates completely, something along those lines. And with the Arrhenius part, it should release H plus. Yes. A compound? A compound would be okay because all acids are compounds. Yeah. Okay. You could say a substance. Okay. A compound. An example of a strong Arrhenius acid, Baran? HCl, yeah. And HCl dissociates completely to form H plus Cl minus. That's how Arrhenius acids behave. Now, for a strong Arrhenius base, we probably don't need to say everything here because it'll be pretty much exactly the same. Yes? So it's going to be all the same stuff, except for that it releases OH. Okay, take a moment, discuss with your neighbor, come up with an example of a strong Arrhenius base. Are you guys ready? Please say no if you're not. John.
Like what is taking space?
An example. Ammonia. No. Senya. NaOH. Because ammonia, can ammonia dissociate and give you OH ions? Can ammonia dissociate and give you OH ions? No, there's no OH in there. Okay? Ammonia is a base, but it's a different kind of base. What kind of base is it? It is a Bronsted-Lowry base. Is ammonia a weak Bronsted-Lowry base or a strong Bronsted-Lowry base? We'll let that one sit for a little bit until we get to strong and weak Bronsted-Lowry bases. Okay, NaOH. NaOH dissociates in water to give you Na plus OH minus, aqueous, solid, and what was I going to say? All strong Arrhenius bases are metal hydroxides. Okay? Oh, that should be a capital A. I guess I should say soluble metal hydroxides. What about a weak Arrhenius acid? So let's define that. Let's define weak. Let's get the Arrhenius acid in there. And then we'll have an example. And always remember, being wrong is good. Why is being wrong good? Why is being wrong good? You fix any misconceptions that you have. We all have misconceptions. If you don't think you have misconceptions, you're fooling yourself. Are we ready to do the weak part? David? Yeah, a chemical species. I'm going to rephrase it just a little bit, but yours is perfectly good. This dissociates partially. Just going to make it a positive statement rather than a negative statement. And we already know the Arrhenius acid part to release H plus. And then I'm going to add a little bit more of the weak part on to release H plus and form an equilibrium. An example of a weak Arrhenius base. or sorry, not weak Arrhenius base, weak Arrhenius acid. Sasha, you don't know? Where might you look to find one? Yeah, go have a look. Page 5. Pick one, anyone. The hydronium ion does count. I'm going to use something else because hydronium is kind of a goofy one. Okay, like just because it's the conjugate acid of water, it's a little bit, you know, it's not like you can. It's just a little bit odd, right? It's different than the other ones. Pardon me? HSO3 minus, yes. I'm going to give something just a little bit less complicated. CH3COOH. Yeah. HSO3 minus, the reason it's a little more complicated is that it is actually amphiprotic. Yeah. So it is a weak Arrhenius acid, but it can also act as a base. So I'm going to go with CH3COOH. And when I write this equation, what should I be writing after CH3COOH? Equilibrium, yes. And then CH3COO minus plus H plus. Those are all aqueous. And it is mostly this and only a little bit that. Now a weak Arrhenius base. Don't worry about these ones. I don't think they exist. I could be wrong, just depending on definitions. What was a strong Arrhenius base? Strong Arrhenius bases were soluble metal hydroxides. Those were our strong Arrhenius bases, right? So a weak Arrhenius base would have to be a metal hydroxide that does not dissociate completely. And when we have a metal hydroxide that does not dissociate completely, a low solubility metal hydroxide, it's not that it doesn't exist, it's just that we don't really think of it so much as a Arrhenius base as we think of it as a low solubility ionic compound. And we actually have a different K value for this because this is a solid and it would dissociate into Ca2 plus and 2OH minus. And that could be like any low solubility compound. Any low solubility compound, you can write a dissociation like this. It doesn't have to be a base, it could be anything. We would use KSP, which is the solubility product constant, rather than a KB, which is the base constant. We will learn all about KSPs in Unit 3, which is coming after Unit 4, very logically. So the main point is don't worry about these ones. No one's going to ask you about weak Arrhenius bases, okay, because it's almost meaningless. We have other language around which we can talk about them, right? Like, so we can talk about them using the language of solubility rather than using the language of acids and bases, Kas and Kbs. We use this other K that we'll learn about in our next unit instead. So I'm just going to put this in brackets. You don't really need to know about it. So don't get too excited about it. Don't spend a lot of time thinking about it, okay? Let us try a strong Bronsted Lowry acid. And this time we're going to start with the Bronsted-Lowry part, the Bronsted-Lowry acid part, and then we're going to do the strong part. Are we ready? No, not yet. Okay. Can we go now? Bronsted-Lowry acid, Tiago. It is a proton donor. And so I'm going to say a substance that, I'm just going to change a little bit so it makes a better sentence. A substance that donates protons. And for the strong part, what percentage of its protons does it donate? 100%. And who does it donate them to? To and you can either say a receptive base, or you can say to a Bronsted-Lowry base. An example of a strong Bronsted-Lowry acid, Sylvia. HCl. Now, how are we going to distinguish this HCl from this HCl? Anyone want to give that a go? Yeah, we're going to add water. Okay, so when you're looking at a Bronsted-Lowry, you need to have something accepting the proton, and usually if we don't mention anything else, you're going to choose water. Okay. And who are our products? We get H3O plus and Cl minus. Excellent. Okay, and if you do a Rice table for this, the water is always going to be like a blank column. Yes? I'm going to say aqueous. Originally, it's a gas, but you'll usually take it from concentrated to more dilute. Yes? Whoa, because I'm in the equilibrium unit and I'm too used to writing equilibrium arrows. This should be a one-way arrow. Thank you so much. Okay, everyone catch that? That should not have been an equilibrium arrow. That should have been a one-way arrow. Oopsie. Thank you for catching that, John. Yes? Yeah, we would normally say that they ionize rather than they dissociate, because this ionization, because it's not really dissociating, right? Dissociating just means splitting apart. And this is more complex than that. You've got the donation of a proton. What about a strong Bronsted-Lowry base? A proton taker, yeah, a substance that I'm going to say accepts protons. And of course, when we say protons, what do we really mean? H plus ions, just to make sure we're not thinking like anything nuclear is going on here. What percent of protons does it take? 100%. It accepts protons 100% from whom? A Bronsted-Lowry acid. Okay, now make sure you've given this a little thought. What is an example of a strong Bronsted-Lowry base? Do we need a little more time on that or no? Anyone need more time on that? Are we ready? Nobody's saying no? Juan? An example of a strong Bronsted-Lowry base. NH3. Excellent guess, but incorrect. Sasha? NH2 minus. So let's go to our data booklet and check that out. We have OH minus and NH3 are the conjugate acids. And so I put acids in quotes here because are they able to donate protons? No, they are not able to donate protons. They are the conjugate acids of the two strong Bronsted-Lowry bases, which are these guys over here. So O2 minus and NH2 minus. So I'm actually going to write down both of those examples because they are the only two. We might as well do both. There we go. NH2 minus, if we put that with water, what do we get? NH3, yep. Plus HO minus or OH minus, yes. While we are here with this one, could you please identify a conjugate acid-base pair in this reaction? NH3 and who? NH2 minus. That is a conjugate acid-base pair. Why is this pen writing so light? Pair. Our other conjugate acid-base pair would be? Who's our other conjugate acid-base pair? H2O and OH minus. That is another conjugate acid-base pair. Who is acting as the acid in the forward reaction? H2O is acting as the acid. That means NH2 is acting as the base. In the reverse reaction, who is acting as the acid? Well, actually nobody, because it doesn't go backwards. But if we had to label these as acid and base, who would we label as acid and who would we label as base? NH3 is the acid and OH minus is the base. Yes? Could it turn into hydronium? Plus H3O plus? You could, it's just not as available as water, so the way more predominant reaction will be with water. Okay, yeah. Because if you think water is just everywhere and hydronium is like 1 × 10⁻⁷ molar. To be fair, the H3O plus is getting used up if you were to take it from a perspective of this equilibrium. You would have your NH2, which could then react here, yes. And then you would end up with what? NH3 plus H2O, which would mean that this concentration would then decrease, which would then shift this to the right, which would produce more hydroxide. But it's all a matter of semantics at that point. It just depends on how you want to express it. Normally, we express it with the water rather than the H3O plus. All right. Out of the two bases here, who is the stronger base? NH2 is the stronger base. That means that OH minus is the weaker base. Out of the two acids, who is the stronger acid? H2O is the stronger acid, and OH and NH3 is, it's the acid. I meant to write stronger, sorry. And NH3 is the weaker acid. Question. Are the stronger acid and stronger base always on the same side? They are here. So for example, if I were to say to you that HA is the stronger acid, let's say these are both weak acids, okay? HA and HX are both weak acids. But let's say that HA is the stronger acid. Is there anything else we can fill in here about who is an acid, who is a base, who is stronger, who is weaker? HX is the acid and it is the weaker acid, okay. And that means that these two guys must be the base and the base. Who's going to be the stronger base and who's going to be the weaker base, and why? Okay, I heard someone say X minus is going to be the stronger base. Why? Yeah, the stronger acid is going to release more protons that will be accepted by the stronger base. The other way to look at it is that the stronger a weak acid, or the stronger an acid, the weaker its conjugate base. So if this is the stronger of the pair of acids, its conjugate base must be the weaker of the two bases. Yes? So if this is our weaker acid, then its conjugate base must be the stronger. So are they always on the same side? Yes. So that's useful to know, because you can always be like, you never have to be confused. You never have to be like, who's the stronger in the thing? They're both on the same side. Once you've identified one of them, you're good to go. Yeah? Which side of the reaction is favored? The stronger side or the weaker side? Have a chat with your neighbor and see if you can convince each other of your point of view. What I want you to do right now is I want you to put a thumbs up if you think you could answer this, thumbs down if you don't think you could answer it, thumbs to the side if you're like, I don't know, maybe I could. Okay, we're mostly there-ish. Okay, well, I'm gonna... Harshika. Yeah, it's gonna be the weaker side is going to be favored. Why is that? Anyone want to try explaining that? Yes, Dylan. Yeah, the stronger side is better at doing its job, at doing the reacting, right? So it's going to react more than the weaker side. Yeah? Okay. You can do like a little drama where like you and your partner can be an acid and conjugate base. I've heard you're going to be the, or not a conjugate base, the weak base. Okay, so I'm HA, you're X minus, okay? And I'm like here. Now he's become HX, yes. But remember, HS is a weaker acid, so is he as good at giving that proton back? No, so where does the proton spend most of its time? It does go back and forth, but where does it spend most of its time? On the weaker side. Yeah? Okay. You should feel fortunate. Sometimes I've had students like chase me around the classroom because I'm like, I'm taking it back. I don't know. I just don't have enough energy for that today, but you know, it's usually quite fun. And they're like, really? Do I have to run after you? I'm like, no. Okay. What have I missed? What have I missed? Okay. Let's say that we have, let's just do this one for example. HCN plus CH3, COO minus. I would like you to predict the products, please. And then tell me, is KEQ greater than 1? Or is KEQ less than 1? First of all, who are our products? Jaden, who would the products be? Cn minus and CH3COOH. Excellent, thank you. And is KEQ greater than 1 or less than 1, Milan? What do you think?
I'm gonna guess.
You're going to guess, okay.
It's less than 1.
And why are you guessing that it is less than 1?
Well, I think the left side contains the weaker acid.
Okay, so you think the left side contains the weaker acid and base. Okay, which, if that's true, KEQ will be less than 1. Okay, now let's check this out and see. We can go to our data booklet. And we can look and we can say, here is acetic acid, CH3COOH, and here is HCN. And we can see just from the position on the table that HCN is weaker. We can also look at the Ka values. If we want to, do some math around it or something, we can say, okay, this one is about, the HCN has a Ka of approximately 10 to the negative 10. And acetic acid has a Ka of approximately 10 to the negative 5. So that means over here we have our weaker acid and our weaker base. And over here we have our stronger base and our stronger acid. So yes, absolutely, reactants are favored. And therefore, KEQ for this system is less than 1. Very nice. Okay. Now we could, yes, sorry. No, you don't. Probably if you were doing something like this on an AP exam, you won't have a table with them listed vertically. So you would just be given the Ka values. So you would have to logic it out that way. But yeah, you don't have to use the Ka values for this one. Okay. Now, you could actually do this mathematically as well if you wanted to, because what you're doing is you are combining HCN in equilibrium with H plus and Cn minus, and you are combining that with CH3COO minus plus H plus in equilibrium with CH3COOH. Yes? If you were to add those two reactions together, you would get our reaction, yes? And we know that the Ka for HCN is 4.9 times 10 to the negative 10. And we know that the Ka for CH3COOH is 1.8 times 10 to the negative 5. So what is the K for this reaction in yellow? Yeah, so the K here is going to be 1 over 1.8 times 10 to the minus 5, which I think is it 5.6 times 10 to the minus 10? I can't remember. 1 divided by 1.8 e negative 5 equals, 1 divided by 1.8 e negative 5 equals. So that's 5.56 times 10 to the positive 4. So then what is the K for this reaction? Yes. Why did we flip it? Because it's backwards. Okay, because we've reversed our reaction. So Ka was that, and so our K of this reaction here is, let's call this 1, I don't know, of reaction 1, whatever. So we flipped it. What would our K for our overall reaction be? Mm-hmm. Yep. Because we're combining, because we're adding the two reactions, we multiply their two K values. And look, KEQ is less than 1, just like we predicted it would be. Yay, you guys. Good job. What's that? Oh, this should be positive 4. Positive 4. I'm so used to putting negatives on the numbers. Sorry. I tried driving home the other day, and I accidentally took the turn where I take my bike to turn because I go home a different route. And I'm driving and I'm in my car and I'm like, this is no through road. I can't go this way. So I ended up having to go turn into someone's driveway, turn around. I'm a very much a creature of habit, right? Like if I've done something like a few times in a row, then all of a sudden it's just what I do. Okay. Now, let us go to page 52. So all the definitions that we've done today are on pages 51 and 52. So we have not done a weak Bronsted-Lowry base, but it would be a species that donates protons to a receptive base, but donates less than 100% of its protons, and it forms an equilibrium. That sentence structure makes me cringe. Like it's not a nice sentence, but you know, sometimes sentences aren't always nice. It does get the point across. Maybe I would say a species that donates less than 100% of its protons. to a Bronsted-Lowry base, forming an equilibrium. That's a better sentence. But would the other sentence get you full credit? Sure. A Bronsted-Lowry weak base, a species that accepts less than 100% of its protons, of the protons from a Bronsted-Lowry acid, forming an equilibrium. And before you read it, tell your partner, what is the definition of a conjugate acid-base pair? Don't read it on your paper, just tell your partner what is a conjugate acid-base pair. What is a conjugate acid-base pair, Edward?
The acid-base pair, so acid and base that differ by one proton.
Yes. Okay, a chemical species that differs by one proton. All right. And we know amphiprotic, yes? A definition, a good definition, would involve having it being able to act as either an acid or a base by either donating or accepting a proton. That would be a good definition. How would you recognize that something is amphiprotic from the formula? Yeah? Has a minus charge. Yeah. Has a removable H. Are there exceptions to that? Who are the exceptions? H2O. And there's one more. There's one that fits that. It has a negative charge. It has a removable, well, does it have a removable H? Yes, it has a removable H. Does it? Yeah, it has a removable H. It has a negative charge, and yet it is not amphiprotic. HSO4 minus. H2O is yes. HSO4 is no. Even though water does not meet the how to recognize, and HSO4 does meet the how to recognize.
These are the only ones.
Those are the only ones, yeah, that don't, like everything else should have a removable H and a negative charge, okay? And everything else that has a removable H and a negative charge should be amphiprotic. We know monoprotic, diprotic, triprotic. Polyprotic just means more than one, so it could be 2 or 3. Yes?
What does this specifically do to negative charge? Why?
So it can accept a hydrogen, an H+.
Would be accepting hydrogen plus the water of using an H with minus.
Hmm? I don't know. That question went over my head. What's the question again?
Was accepting an H plus, what is this already got the positive charge, the harder than using an H plus?
Yes. If you already have a positive charge, you would repel H pluses.
Yeah.
Yeah.
But when you have a negative charge,
But when you have a negative charge, it would like to accept an H plus.
no, but this isn't attract the H charge.
Yeah, but there's other factors involved as well. So say, for example, with the HCO3 minus, HCO, oh, sorry. With the HCO3 minus, you have electronegativity here, and electronegativity here, and electronegativity here, high electronegativity in those three places. So basically what's happening is all these guys are pulling electrons, which then makes it possible for this to fall off and leave its electrons behind. Yeah? Yeah. Plus, if you have a resonance structure where you have the, when it's left behind, you actually have three resonance structures. You've got C, O, C, O, C, O. Yeah. You have this extra pair of electrons. Is that correct? Yeah, that's correct. Okay, so this extra pair of electrons is delocalized over three areas. Yeah, which means that if you've got extra negative charge spread out over more areas, that is more stabilized. So we say that this conjugate base of HCO3 is more stabilized, yeah, than it would be if it didn't have all those places to go, which is why this can donate its hydrogen. It's not a very good acid. HCO3 minus is a pretty weak acid. Okay, it's like on the low end of the scale. Yeah? Yeah. Okay, how are we doing? We're okay? All right. We are going to go to page 54. Oh, no, we're not. I forgot something. Sorry. We're going to go to page 53. For your quiz, you should know the properties of acids and the properties of bases. And there are 5 that you need to memorize at this point. And they spell, if you take the first letter of each of them, control, C-T-R-L, control R, and C-T-R-L, control F. So C stands for conduct. They both conduct electricity. They are electrolytes. Do you guys remember the term electrolyte? Yeah? Maybe? Electrolytes are substances that conduct electricity because they have freely moving ions. Yes? So both acids and bases are electrolytes. That's the one that they have in common. The next 3, the T for taste, the R for what it reacts with, and the L for litmus, those are different. Okay, so they taste sour for acids, they taste bitter for bases. R is for reacts. Acids react with bases, bases react with acids. We get to the L. L is for litmus. Acids turn litmus red, bases turn litmus blue. If you forget that, B for base, B for blue. And finally, there's the two properties that have nothing in common with each other, really. Acids react with some metals to produce H2 gas, and bases feel slippery. Okay, you should just be familiar with those. Yes, and that's about it. Okay, and now we're going to page 54. And we're going to talk about the difference between strong versus concentrated and weak versus dilute. Strong and weak have to do with how much the acid ionizes. Concentrated and dilute have to do with the number of particles in a given volume. So basically, concentrated is to do with molarity, and dilute is to do with molarity. Strong and weak have nothing to do with molarity. Does that make sense? Strong just means it ionizes completely. Weak means it ionizes partially. Concentrated means there's a lot of particles in a volume. Dilute means there's not very many acid particles or base particles in a given volume. So far, so good? Okay. So you can have a solution that is strong and concentrated, or a solution that is strong and dilute. You can have a solution that is weak and dilute, or weak and concentrated. They're totally separate things from one another. In terms of conductivity, strong acids are more conductive than weak acids. And that's because strong acids ionize 100%. Weak acids typically ionize between 1 and 10%. So if you are given a strong acid and a strong base of the same concentration, the strong acid will generally have a 10 to 100 times larger ion concentration. So if you look at this, we have here 3 acid particles. And we end up getting 6 ions, because this is a strong acid. This is taking it down like really simplified, so it's numbers we can see. This is a weak acid, and we have 3 acid particles, but only one of them has dissociated, so we only get 2 ions. So it's much less conductive. Generally, when it comes to conductivity, it matters more whether it's strong or weak. Than whether it is concentrated or dilute. That doesn't mean that concentrated and dilute can't make a difference. Because if you get a weak acid, you can make it very concentrated. And you can take a strong acid and make it very dilute. And if you do that, the two of them might have the same conductivity. Does that make sense? Yeah. You can calculate the concentrations. So you would, for a strong acid, you calculate its concentration by simple dissociation stoichiometry, right? And then for a weak acid, you will calculate the concentration using a Rice table. Yeah? So that's basically how we're going to do it. Yeah? And we'll get into the math in section 4.3. Yes? You would be able to, yes, absolutely. So you'd be able to say this one has this much ions, this one has this molarity ions, this one is the better conductor. But, you know, a typical question might be, you have a strong acid and you have a weak acid, and they both make the light bulb light up the same amount. How is that possible? Right? And you'd need to say that the weak acid would have to be sufficiently concentrated and the strong acid sufficiently dilute that the ion concentrations end up being that relatively the same. Yeah? And I think that's as far as I got with my other block, which is good because we're basically out of time. So let's give you today's homework, which is, if you did not do pages 48 and 49, although those were for homework on the weekend, you can do those. You should now add on number 50, page 50. And then 60 to 64 is a review of everything that you need to know for Thursday's quiz. Yes, you've got a quiz on Thursday? Okay. So if you don't get through all of 60 through 64 tonight, that's not the end of the world because you do have until Thursday, but get a start on it, okay?